Okay, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, Bapak-bapak, Ibu-ibu, ladies and gentlemen. Okay, welcome to our webinar. Today we are lucky because we have Prof. Andrew Charleson. I think Prof. Andrew Charleson is the one that one of a professor that deal with the architecture and structural system. Maybe a little bit I introduce Prof. Andrew Charleson. Prof. Andrew Charleson is a professor. I will open a little bit about him. He came from Wellington School of Architecture. And now I think he already retired. Because of his retirement, then he has chance to visit us as well. He was one of our visiting professor last semester in Universitas Islam Indonesia. And you know that Professor Andrew Charleson has many publications related to structural system and architecture. If you open in internet, you may find ton of books and papers. So we are lucky here to have him and to hear from him, one of the top scholar in the world, I think, isn't it, Prof. Andrew Charleson? So thank you very much. You give us your time to give your lectures today, next week, and after Idul Fitri Bayrams. So thank you very much. We will have 3 serials webinar about the structure and earthquake. And the second one, we are lucky as well. Today we have Professor Widodo from Civil Engineering, Faculty of Civil Engineering and Planning, Universitas Islam Indonesia. So he also one of scholar dealing with the earthquake. And you may find a ton of publication as well written by Professor Widodo. So I think to say hello, please, Prof. Andrew Charleson and Prof. Widodo, and then we start your presentations. Please, Prof. Andrew Charleson.
Selamat siang. Saya senang sekali bertemu dengan Anda hari ini. Maaf, bahasa saya belum lancar, jadi saya harus berbicara dalam bahasa Inggris. It's very nice for me to be here, and I look forward to sharing, well, my passion with you, which is about designing works of architecture for earthquake forces. Could I just ask you, Professor Noor, can the participants ask questions during my presentation?
Yes. For participants, we suggest them to write in the chat about the question, and I will read for you, Prof. Charleson.
Yeah, great. Okay, because from time to time during my lecture, I will pause and we can see if there are any questions for me to answer as I proceed.
Oh, okay, as you wish, I will read for you.
Thank you.
Okay, thank you, Prof. Charleson. And then Prof. Widodo, please, saying something to our participants.
Pak Noor. Oh, okay. Okay. Anyway, thank you very much for all participants. Today we have kind of webinar. Yeah, we're talking about architectural design for earthquake resistant design that actually connecting with civil engineering subject. So I'm very happy to be invited Pak Noor and we meet again with Professor Andrew. Thank you very much and welcome to our webinar. Thank you.
Thank you very much.
Thank you very much, Prof. Widodo. So, Bapak-bapak, Ibu-ibu, sebelum kita mulai, Prof. Charleson Anderson, let me talk in a little bit in bahasa. Oke, Bapak-bapak, Ibu-ibu sekalian, selamat datang sekali lagi. Kami ucapkan kepada Bapak-Ibu sekalian. Seperti biasanya, kami memang berusaha untuk membuka akses universitas, khususnya di jurusan arsitektur ini, seluas-luasnya ke publik berkaitan dengan banyak hal, terutama di masa COVID ini. Semoga apa yang kami lakukan ini bisa sedikit memberi sumbangan ilmu pengetahuan kepada kita semua. Dan upaya yang sedikit ini memang kami dedikasikan juga untuk kemanusiaan, karena seperti kita ketahui bersama bahwa negara kita dikelilingi oleh ring of fire yang mana membuat gempa bumi setiap saat bisa terjadi dengan kapasitas intensitas yang besar. Barangkali tidak kita harapkan, semoga tidak terjadi, namun jika itu terjadi maka kita harus siap. Oleh karena itulah we have Professor Andrew Charleson today, and we are lucky because he is dealing with the architecture and structural system. As you know that many of architecture lectures or even the student themselves, if they ask to talk about the structural system and especially about the earthquake, maybe they will think that, oh, this is my burden, this is too heavy, and so on and so forth. But I think that's not good for us, since we are living in, ring of fire through our countries, just like New Zealand, isn't it, Prof. Andrew Charleson? Japan as well. So
indeed,
that's why let's talk about that. And we are lucky once again we have Prof. Andrew Charleson today, who are willing to share his knowledge and experience to us. So please, your time, Prof. Andrew Charleson.
Okay, thank you very much for that very nice introduction. And good afternoon, everybody. I'm very pleased to spend this time sharing my knowledge and experience with you. So I'll start my presentation and I'll just share my screen. I just need to adjust the view. Okay, there we are. Can you see that okay?
Yes.
Okay.
Yes.
Can see clearly.
Okay, well, thank you. So that's the topic of my talk, architectural design for earthquake. And in fact, this presentation is very, very similar to the one I gave at UEE in September last year. want to begin by just reminding you that, like myself, you live in a very seismically active country. And this slide shows earthquakes over about a 20-year period from memory. And it doesn't show the latest earthquakes for the last 5 years or so. But you can see that right throughout Indonesia, particularly on the edges of the tectonic plates, many, many earthquakes occur. And really, there's a chance of quite strong shaking in almost all areas of Indonesia, with the exception, perhaps, of large areas in Kalimantan. So I'm just going to get my mouse. Can you see my mouse?
Yes.
Yes,
sir.
sir.
Yes,
Yes.
Thank you. Yeah. So within Indonesia, Kalimantan is like the safest place, really. And then I suppose it's the east coast of Sumatra. But everywhere else, you can see there's a high number of earthquakes, and therefore there's a high earthquake risk involved. Now, when we come to designing buildings to resist earthquake, we can think of the process as being like a chain. And a chain has many links, and every link has to be strong. If one link is weak, then the chain will break and our building might collapse in an earthquake. And so the first thing that we have to do as designers is to design the configuration in a satisfactory way. By configuration, I mean the structural layout of the building. Then, after architects have attended to configuration, often in conjunction with the civil engineers will do the analysis. Then they are responsible for the design and detailing. And then, if at all possible, the civil engineers' plans have to be supervised on the site so that the design is built properly. So I'm going to begin by talking about the structural layout or configuration. And I'm beginning by talking about the configuration of vertical structural elements like columns and walls. And the first principle, I'm basically going to give you a number of simple principles that we as architects and engineers use to assure ourselves that our buildings are going to be earthquake resistant. And so the first principle that we must always apply in any design is to provide earthquake resistance in two orthogonal directions. And so why do we need to do that? Well, if we look at the diagram at the top of the slide, we can see the axes, the x-axis and the y-axis. And just imagine for a moment that the earthquake strikes the building at an angle. And like this represents the vector of the earthquake attack at an angle. Now, a very good way to resist that earthquake attack is to provide enough strength in the X direction and enough strength in the Y direction. If we have strength in both directions, that means that we can withstand earthquake attack from any direction. And so in this very simple plan here, in the Y direction, we've got two structural walls that are strong in this direction. And in the X direction, we've also got two structural walls that will be strong in the X direction. And because we've now got strength in the Y direction and the X direction, then it doesn't matter what direction the earthquake attacks, because we've got these two components of strength in each direction. So this is the first principle for sound earthquake resistant design in architecture. We must have resistance across the building, and equally, we must have resistance along the building, okay, in both orthogonal directions. Now, before I move on to some of the structural systems that we use, I just want to say a few words about post and beam structures and structural walls or load-bearing walls. Now, many of us are well used to post and beam structures, and theoretically, a post and beam structure has two posts and one beam. And at the top and bottom of the posts are pin joints, pure pin joints. Now, a post and beam structure is great. It's excellent for withstanding gravity loads. However, when it comes to a horizontal load, as would occur during an earthquake, a post and beam structure is totally unstable. It has no strength at all. And so it's important to recognize that particular limitation of post and beam structures. Now, what about load-bearing walls? They are also very, very good at resisting gravity loads. And I suppose most of the houses of Indonesia use load-bearing walls to resist the weight of the roof and so on. And that's fine. But when load-bearing walls are subject to forces at right angles to their length, like this, then they too are unstable and they generally will collapse. However, even though they are very unstable and unsafe against these forces, load-bearing walls can be very effective in resisting forces parallel to their length. And of course, walls like this, as I mentioned, typically form the main structural elements of the typical Indonesian simple house. So when it comes to resisting earthquake, us engineers and architects, we have some choices to make. And I'm always surprised at how limited our choices are, because when we are designing to resist earthquake, there are basically only 3 structural systems that are capable of resisting earthquake forces and movements. There are only 3 really. And so our job as designers, your job as students who are working on your design projects at the moment, your job is to choose one of these structural systems in each of the primary directions of your building plan. And so what are your choices? You can choose structural walls or shear walls. You can choose braced frames, or you can choose to resist your earthquake forces using moment frames. The choice is yours. And normally you will make that choice based on your design concept, you know, your big, exciting design idea, and the program of the building. Those are the 2 things that should influence your choice of structural system to resist earthquake. And as I said, you've got to choose one of these structural systems for each direction of your building. And it is not wise to mix them. Like in one direction of your building, you should choose just one system. And in the other direction, you can choose the same system or another system. But you shouldn't use 2 systems in one direction. Why? It's like mixing colors when you're painting. You know, if you mix various colors, you can easily end up with a mess, a color mess. And so we try and keep things pure. And we do that by just having one system in one direction. And depending on the size and the height of your building, you need as many elements as are necessary. Like, for example, in this upper diagram, I've got a building with shear walls in each direction. And you'll notice that in each direction, there are just 2 shear walls. Like in the X direction, there's this shear wall and that shear wall. In the other direction, this wall will be effective and that wall will be effective. But if you're designing a very large building, you might need more than 2 shear walls in each direction. You know, you might need 5 or 10. And you can choose how many you need and how long they need to be. And I come to that later. And so I'm going to begin by talking about shear walls, just giving you some information about them so that you can be a bit more confident using them in your designs. And so, I mean, this is what a shear wall looks like. Its job is to spring from the foundations. The shear walls need strong foundations, and then the shear walls need to rise vertically right up to the roof level. So the shear wall must be vertical and it must be continuous, and it connects to each floor. Each floor is strongly connected to a shear wall. So here is the typical beam that a shear wall will need. Often they will need piles, say tension piles, to stop the shear wall overturning. Here's the shear wall here. Here are the floor slabs that are connected to it. A shear wall will have quite small openings. But if there are large openings in a shear wall, such as for circulation, then we would call this shear wall a coupled shear wall, because the openings are quite large, and we would have these large coupling beams with special reinforcement coupling or tying together the two wall elements of this coupled shear wall. Now, you're pretty used to shear walls in domestic construction in Indonesia, particularly when you are using confined masonry construction. I think many of you will be aware of this type of construction where you lay your masonry walls and then you cast your practical columns and your ring beams, your tie beams. This type of construction uses walls to resist earthquake. And it is like almost the opposite of an RC frame with infill walls. They're totally different structural systems. And so if we are using shear walls out of confined masonry, we need to have vertical tie columns and horizontal tie beams to tie everything together. And so here's the masonry, here's a tie column, and these are the recommended sengkang or ties that we need in different structural members. Here's a confined masonry apartment building being built in India, actually. Here's the masonry, here the tie columns, here in this third level, they've laid the bricks for the wall and they've yet to cast the tie columns. So this is a very good design. This particular wall is very effective because it's got no openings. Because you see, during an earthquake, a confined masonry wall experiences earthquake forces at the top of the wall. And those forces need to go to the ground, and they do so through compression on the diagonal in the wall. And as these forces go to the foundations in compression, for equilibrium, there is also tension in the practical tie column. That's why we call it a tie column, because it has tension in it, which of course is unusual, and that only happens during an earthquake. And so if we've got walls in our buildings that we want to use to resist earthquake, we can't have big openings. That's impossible, because if there are big openings, that means that the compression forces on the diagonal can't get through. The building will be very weak and very, very severely damaged. Now, there are references explaining this type of construction. And if any of you are not very familiar with it, then I would encourage you to look at some of your own Indonesian references, like this poster here in Bahasa Indonesia, and other authors in Indonesia. Public Works Department got material to guide you about confined masonry shear walls. Here's another very good guidebook, guidelines for building earthquake-resistant houses in confined masonry. Just before I talk about braced frames, I just want to say that shear walls can be of a number of different materials. Like I've mainly been talking to you about masonry shear walls, confined masonry walls. But it's also possible to have shear walls out of reinforced masonry. That's quite popular in New Zealand. Or you could have walls even out of plywood if you are designing a wooden building. But for medium to high-rise buildings, we would use reinforced concrete as the material of our shear walls. And so that would be what we would use for buildings over probably 2 or 3 stories. Shear walls are really the best form of structural system to resist earthquake because they can be the strongest and the stiffest structural system. And so if possible, as designers, you should try and find places in the plans of your designs where you can insert structural walls. If you can resist your earthquakes using structural walls, then your columns, the gravity forces, they can be quite small and very slender. The next system for resisting earthquakes we call braced frames. And these frames can come in different geometries and using different materials. Usually, braced frames have steel bracing. There's nothing to stop you having reinforced concrete bracing for cross-braced frames, inverted V-braced frames, and diagonal braced frames. But for these other frames here, we've got to use steel as the bracing elements because we create special, what we call fuse regions to absorb the earthquake energy. And so as a designer, you can choose cross-braced frames to resist earthquakes in a building you design. And in consultation with your civil engineer, you can discuss what types of cross-brace would be best for you. So that's the second best option for resisting earthquake. And the final option for resisting earthquake is using the structural system we call moment frames. And this diagram just shows us the key aspects of moment frames. First of all, columns, then beams, and very importantly, the columns and beams are connected using strong and rigid connections. Every joint must be a rigid joint. So let me talk about moment frames for a couple of minutes. First of all, when you are using moment frames, you've got to have the orientation of the columns done correctly. Like see this moment frame at the top of the slide. It is a moment frame like in the X direction because that's the direction of the beam. And therefore the columns, they should be strong in the X direction. But see how this particular column is weak in the X direction. It is strong in the Y direction. So it has the incorrect orientation. if we've got a steel moment frame, the frame is going to be strong in the X direction, and therefore the steel columns, they also have to be orientated to be strong in the X direction, but these are not. These are strong in the Y direction, and therefore they are incorrectly orientated. So here is an elevation of a typical reinforced concrete frame. This is a 1-bay, 1-story frame. What are we looking for in a frame? Well, first of all, we need to have quite a deep column. You know, we can't have a skinny little column to withstand earthquakes. We need a column with sufficient depth to it. And also it has to be quite thick. We need to have a beam that's quite deep, a bit deeper than just for resisting gravity forces. And here we need to have our beam column joint that is strong and rigid with lots of special reinforcing steel. If we look at a cross section through the beam, section A, we can see this is the beam depth, and it usually includes the thickness of the slab that contributes to the strength of the beam. Now, moment frames, they can be made from different materials. I've showed you a reinforced concrete frame, and I've showed you, well, a steel frame that is incorrect. This is the correct layout here. But moment frames can also be of wood. And if you've got a lightweight wooden building, then you can use wooden moment frames. The only trouble using wood is making sure you can achieve a rigid beam column joint. That's the main challenge using wood for a moment frame.
Prof. Andrew, before you continue, somebody ask something?
Yeah, okay.
Okay, because it was about the building envelope from Pak Budi to Prof. Andrew. I have a question about architectural trend nowadays that all high-rise building use curtain wall system for building envelope. Is this type of wall is one of important aspect on designing earthquake building, as the glass on curtain wall can break when earthquake and falling into people walking on the ground level? Okay, that's the questions.
Okay. Well, thank you. That's a really good question. Curtain walls are certainly very popular on many high-rise buildings. And I'm pleased to say that in recent earthquakes, curtain walls have shown a good track record. In other words, they've performed well during earthquakes. And the reason is that if a curtain wall is designed properly, the designers allow a gap between the glass and the aluminium mullions of the curtain walling, so that when the building moves to and fro during the earthquake, the glass moves within the frame and it doesn't actually hit the frame. And so there's no breakage. And so if a curtain wall is designed to accommodate the movement of the building, which the engineer can calculate, then the curtain wall is perfectly safe. And it's a very good system to use because it's so light. And therefore, you know, I don't see any problem at all. I would recommend using curtain walls if you wanted to. Are there any other questions?
For now, that's all. We're still waiting for others. Thank you, Prof. Andrew.
Okay. Okay, so just to finish off moment frames, as designers, you choose as many frames and bays as you want to suit your concept, your design concept and your program, but to avoid the members being too large. Like I've got a couple of examples here. Both of these buildings have been designed to resist earthquake. And in the left-hand building, in the Y direction, the building withstands earthquake using 2 frames, and each frame is 1, 2, 3, 4 bays long. Okay, so in this building here, we've got 2 frames, 4 bays long, withstanding forces in the Y direction. In the X direction, this building resists earthquake with 2 shear walls. But I just want to talk about frames now. Now, as the designer, we can choose how many bays we want. And like, here's another option that works for this building. In this design, there are just 2 frames, 1 frame here and 1 frame there. And each frame has only 2 bays. So obviously there are fewer columns. And so for this building, the columns will be somewhat larger because they're fewer. But you can see how these frames can be placed anywhere in plan. Like this frame is at this end of the building. This frame is at the other end of the building. It doesn't matter. The frames are strong in the Y direction. And that's all that counts. And so if we wanted to, we could design a building just for a single bay frame. But of course, if we did that, the columns would be very large. You would have to decide whether or not that was acceptable to your architectural design. So as architects and engineers, we have an infinite number of options when it comes to how we design our structures to resist earthquake. Although we've only got 3 systems to choose from, we can have choices within each system to give us, as I say, an infinite number of options. And so surely we can design an option to suit our design concept and to suit the program of the building. If I just elaborate, let's look at the shear walls. Like, I mean, in these buildings, I haven't put much effort into the shear wall design, but I've just designed 2, and they are strong enough to resist all the earthquake in the X direction. Now, if I had wanted to, I could have used 4 shear walls, maybe 1 there and 1 there. And if I used more shear walls, then the length could be reduced a little. And so we designers have a lot of freedom and flexibility in our choice of these structural systems. Now, I'm hoping some of you might have a question about what I've been saying, because I think some of what I've been saying is rather different from a lot of practice in Indonesia at the moment. So if you've got a question, just type it in, and I can be interrupted.
Yes, this is from one of us, from Ibu Irma Nasution, Prof. Andrew. He asking about the traditional house, which is using wooden structures. And on the joints, there is not kind of rigid construction, but flexible constructions. And the buildings still stand with the earthquake. What about your opinion about this, Prof. Andrew?
Yes, well, that's a really good question, thank you. You're talking about a traditional house that's relying on frame action to resist earthquake, because perhaps there's no diagonal bracing. And so all the forces have to be resisted by these rather flexible frames. And as you've pointed out, the frames are particularly flexible because the joints, we might call them semi-rigid. They're not totally rigid, are they? They're maybe semi-rigid. So they've got strength. The joints have got some strength to resist the bending moments, but they're pretty flexible. And so what that means is that during an earthquake, your little house is actually very flexible for earthquake movements. And if your house is built on the rock, that means that the flexibility of the construction will be an advantage. Your little house will experience less shaking. However, if your house is built on soft soils, then the flexibility of your house will actually cause it to resonate, and it will get far more badly damaged. But if we go back to the house built on rock, it is flexible, and therefore it may survive the earthquake, but it probably will suffer a lot more damage because of its flexibility. It's going to move more. It's going to move to and fro further than a stiffer house. And therefore, I would expect a lot more damage. I'd expect windows to break. I don't know what the infills are, but they are going to get damaged. Or maybe the infills are just woven bamboo, bilik, maybe, in which case there won't be a problem because they're just so light. So yeah, those are the things I'd like to say in answer to your very good question. Thank you.
Thank you.
Noor College, do you hear my voice?
Yes, Prof. Widodo, please.
Professor Andrew.
Yes.
I'm sorry because I have technical problems several times, you know. So I just making reconnect again and reconnect again. I'm sorry, but this is in practical habitual in Indonesia, particularly in the low-rise buildings, such as presented in your slide, 4, 5, 6 stories, and so on and so on. Normally in Indonesia, we don't use shear wall or structural wall. We just use frame. I don't know. This is maybe a or low-rise building, normally we just use a frame as a structural system, because maybe constructing structural wall in Indonesia is not easy, and also the people may assume that structural wall is more expensive rather than a frame. And thirdly, like what you said, that structural wall, it needs a very strong foundation.
Okay, well, look, thank you for those observations. And I mean, I agree with you that shear walls are not used very often in Indonesia, but sometimes they are used. But experience from every other country in the world suggests that shear walls are the best method of resisting earthquake forces, because they are potentially the strongest and the stiffest. And also, they're not so sensitive to construction problems. Like, I mean, I've observed many frame buildings in Indonesia under construction, and I haven't seen a frame building that complies with the Indonesian code yet. And therefore, frames are very sensitive. You know, if you leave out some of the stirrups or ties in a frame, that is very, very serious. If you don't have any joint, if you don't have any shear reinforcement in the beam column joint, which is often the case, then the building will not, that frame will not perform very well at all. It'll get so flexible, it'll just cause so much of a problem. And so frames are very, very sensitive to design and construction. That they're very sophisticated structures, actually, frames. And so my recommendation is that if at all possible, designers should use shear walls that are a lot more reliable. And I agree, they may cost more money, but remember, if you use shear walls, then you can save money on your gravity frames. And so there are some savings to be made. But I take your point that shear walls are not the most popular system in Indonesia at the moment. But I'm trying to encourage you by giving you really what is the best practice internationally. Is that okay, Prof. Widodo? Well, are there any other questions, or shall I continue?
Not yet, Prof. Please continue.
Okay. Now we come to another principle of designing buildings to resist earthquake. And this principle is in order to give our building resistance against torsion. You see, during an earthquake, when the ground is shaking, every building twists in plan. And so in order to stop a building twisting too seriously, we must apply these rules here. We must separate parallel systems in plan, and we must have a minimum of 2 structures in each direction. So take the X direction here. We've got a structural wall, or this could be a moment frame. Imagine this is a moment frame here and a moment frame here. These moment frames are separated in plan. by this distance, and therefore they are very able to resist torsion. In the y direction, may call this a moment frame there and a moment frame there. Here's the separation distance. And so the building is able to withstand twisting and shaking in the y direction. And so this is a principle that each of us designers must always put in every single building. We must have two structures in each direction, and they must be separated in plan to withstand the torsion. And so those are the only principles you need to apply to have a good earthquake resistant building. So that's all the principles that there are. And so now I come to this question, and I hope that you would like to ask me this question for the buildings that you are designing at the moment. How much structure do you need? How many shear walls do you need? How many frames do you need to resist earthquake in each direction? This is the critical question for every designer. And so to help you answer that question for your building, I've helped develop this software called Resist. And it is what I call a rule of thumb software. It's not sophisticated like the software civil engineers use. This is software for architects because it doesn't need any calculations. And you can download it free from that website. And so what I'm going to do now is, well, in a minute, I'm going to demonstrate the software to you. But before I do that, I'm just going to pause for a couple of minutes. Maybe you want to go and get a cup of coffee or a nice cold drink.
We're fasting here, some of us. Okay, Prof. Andrew, there is a question from Pak Wahyu Puana Putra. He asking about seismic principle in your book. There are, if not wrong, about 4 principles to deal with the earthquake, which is strength, stiffness, torsion, and force paths. So for the non-engineered buildings, which one is more important, strength or stiffness? Thank you.
Well, for non-engineered buildings, I think the strength is important. Strength is more important than stiffness because we've had a question from a previous participant about, you know, how flexible traditional houses can perform quite well in earthquakes. And that's true. And so any building has the potential to perform as long as it's got enough strength. You know, if it's too weak, then the columns or the walls will just snap and the building could partially collapse. But we are looking, the primary thing is to get strength. And for non-engineered construction, the strength comes from those confined masonry walls without big openings. That's what we need. And of course, those walls need to have their tie beams, their ring ballocks to tie them together, and then they should perform okay. So thank you for that question.
Okay, next still from this one from Pak Budi. To Prof. Andrew, in your example, all the earthquake resistant structures are located on the perimeter. How is about we put the location inside the building, for example, as the shaft or lift? And how is about we put the shear wall on the edge of the building, as normally we don't want any closed wall in the middle of our elevations?
Yes, well, those configurations are very possible. There's no need to put frames on the perimeter. In my own country and probably some other countries, designers prefer to put moment frames on the perimeter because of the depth of the beams. Because if you put those frames inside the building, then they can disrupt the mechanical services. You can have problems with integration of your, ventilating systems. And so from that point of view of integration with services, it's quite a good strategy to have your frames on the perimeter of your building. The other advantage of having them on the perimeter is that that's the best for torsion. So if you're going to put your walls or frames inside around a shear core, say, or forming a shear core, that's quite possible, and that's very common. You just have to be aware that the building will be more flexible for torsion, but it's quite possible. And so, that designers often use that method of putting the shear walls within the body of the building.
Okay. I think that's the questions. But Widodo, do you have comments for these questions? Prof. Widodo? I think is in and out because of signal quality, maybe not good in his area. Okay, Prof. Andrew, what about the combined structural system in non-engineering building, such as in Jogja, for example? You know what kind of traditional houses in Yogyakarta. When earthquake struck in 2006, there are many casualties. There are many thousands of buildings collapse. From our traditional building, not so traditional actually. It's constructed from wood frame and brick wall. So that's create a problem for us. What is your opinion about that?
Yes, well, that is a problem because, as I explained to you, when a wall has loads or has shaking at right angles to its length, a wall is very weak. And especially if the wall is not tied to any columns. And so if you have a wooden frame with brick walls, there's usually not a very good connection between the bricks and the wood, the wooden frame. And so it's very easy for the bricks to, fall from the wall. that wall is very unstable because it isn't strongly tied with practical columns and ring beams. And so everywhere in the world where we have houses with unreinforced brick, well, it's very unfortunate, but those houses are not particularly safe in an earthquake.
Yes, yes. Unfortunately, yes. And that was because of massive construction starting from the Dutch when they tried to replace a bamboo and a wooden wall by brick walls. And unfortunately, the technology was not absorbed well, and maybe because of economical situations, they cannot afford build a strong wall, maybe. And then it was happened like that when 2006 earthquake strike, and then thousands of buildings just collapse. And another question, Prof. Andrew, is about any from, I don't know, from WUS, from Lenovo. It's not mentioned, or from Pak Bambang. In earthquake design, we can use three systems of rigidity: shear wall, brace frame, and rigid joint. Can we use combination of this system in one layer? For example, one side we use shear wall, and the other side we use brace frame.
Yeah, a very good question. And the answer is no, we can't, because we must only have one system in one direction. Otherwise, the force paths in the building become very confused. And if, for example, we did have shear walls in one place and frames in the other place, the building would suffer severe torsion because the shear walls are a lot stiffer and stronger than the frames. And therefore, during the earthquake, the building would twist really badly and, you know, it would suffer serious damage. So the principle of one system in one direction is very important to follow. There's only one situation where designers in the world don't follow it, and that is for very high-rise construction. If you have a building over, say, 15 stories, then it is economical and safe to have shear walls in parallel with moment frames, but only for very high-rise buildings. Otherwise, it is not recommended.
Okay, thank you, Prof. Andrew. From Pak Nasruddin Junus, there are three ways to reach a good performance building in earthquake. 1, increase the strength. 2, increase the ductility. And 3, reduce the seismic input motion into buildings. According to you, which is the best?
This is a nice question, and the answer is very simple. The best method is to reduce the earthquake input into the building using seismic isolation. This is the best method of resisting earthquake, but it is expensive. It is more expensive. Not by a huge amount, maybe by between 2 and 10% of the structural cost. But the best method of earthquake resistance is, as I say, seismic or base isolation. But I'm not discussing that today because it is quite rare to use that, even in more developed countries. Most buildings don't use isolation unless they are hospitals. And in countries like the US, Japan, and New Zealand, and maybe Chile, most new hospitals these days are seismically isolated.
Okay. Okay, that's all, I think, for the question, Prof. Andrew.
Okay, well, I'm going to change my software here. So if you just please a patient. Oh. Excuse me, I just made a mistake. So I've got to go back to my desktop. I'm just going to have to spend a minute here getting
Okay,
sorted.
Prof.
Sorry.
Okay, takes your time.
Yeah.
We don't have Prof. Widodo yet. He's not come back yet, unfortunately. Okay, thank you, Prof. Aldrin. Yeah, there is a question, but I think I will read later on.
Yeah, thank
after
you.
Prof. Andrew find his presentations. Yes, another one from Pak Hakim. Please write your question here.
Now, can you
Okay.
see?
Yes, we can see, Prof.
You see my software? Okay, so I'm going to introduce you to the software for two reasons. First of all, so that you can see how we apply these earthquake principles. And secondly, so that you have got a tool that you can use to design your own earthquake resisting structures. This software is called Resist, and it's available for free. And I gave you the link before on one of my slides. The software comes with some help. It's got a tutorial and other information about the program, the software that you can look up. So there's a lot of help there. And actually there's a YouTube video of me demonstrating it that you can get from YouTube if you search Resist and maybe Charleson. And so when you open Resist, you get this very simple building, which is not a work of architecture, but is just a very simple building that we transform into the building that we are designing. And so let's design a building together. First of all, we have to put in the importance category. Like if we've got a normal office building, it's a normal structure. If we've got a hospital or a police station or a fire station, it would have post-disaster functions. If we're designing a movie theatre or a shopping mall, maybe we would use this. But let's design a normal building today. How many stories? Resist can go up to 8 stories maximum. The story height of your building, let's say 3.5 meters. The height of the roof, say 2.5 meters. Now we have to tell the software the weight of the construction elements. What is the weight of the floors of our building? Well, that's a lightweight floor, wood. This is a medium weight floor, steel formwork. And this is a heavy floor, solid precast concrete or precast slabs. So usually in Indonesia, you use heavy floors. So we'd go heavy. The floor live load. Let's say we're designing an office building. Office. What about the weight of the interior walls? If you're using bricks for the interior of for the partitions and so on, maybe it would be medium. And what about your cladding? If you're cladding bricks, it would be medium or heavy. If your cladding is a curtain wall system, it would be light. So let's choose light. And the weight of the roof, let's assume that's a concrete slab, it's heavy. So now we've told resist our construction weights. Then we go to the floor plan. Now, our building that we're going to design today is going to be rectangular. And let's say it's going to be 40 meters by 20 meters. And so the program has a default option of shear walls that we will change. Now, if we right click, we can add points. And when we add points to our plan, we can create different geometries of our building. And so resist enables you to design some quite complicated floor geometries. So let's say our building is like that. But the floor plan can be of any polygon that you want. I'll make it a bit more. No, I won't do that. Add a point there. Let's make it like that. It's rather irregular, isn't it? No problem. So that's the shape of the building we're designing today. It's what some designer might think is a wonderful work of architecture. Okay, so now we go to the floor, we go to earthquake. And we have to put in the hazard factor. Now, for Jakarta, the factor is 0.4. For Jakarta, I don't know, it might be 0.3. For Bandung, I'm not sure, it might be 0.3. But Yogyakarta is in a more active area, and so the hazard factor is greater. Then this map here, this just applies for New Zealand. So it's no use to you. So don't worry about that. Now the soil type is very important. If we're building this, say we're building this building near the UEE campus in Yogyakarta, then I would say we probably have medium soil. So that finishes the earthquake design. Now we go to the wind loads. And if we've got a heavy building, the wind will never be critical in Indonesia. And so you don't need to worry about wind. So we just leave that. And now we come to where the fun begins, where we design the structure for the X direction, like this direction here. Now at the moment, our resistance in the X direction is by 2 shear walls. Well, what are the choices? Now in the X direction, we've got 3 choices that I've already explained to you. These are our 3 structural systems that we can use to resist earthquake. Now, just for interest's sake, I'm going to use shear walls in the X direction for you. So structural walls, we've got a choice of material, reinforced concrete masonry, which is rare in Indonesia, and plywood, which is not appropriate because our building is very heavy. So we choose reinforced concrete. Then we choose how many walls we've got. Well, let's have just 2 walls, but let's make them part of a core. Okay, so in the X direction, we're going to resist all our earthquakes on these 2 walls in the core of our building. Now, when I look at these shear walls, they look very skinny to me. They look too flexible. And so I'm going to increase their length to make them more realistic. Say 7 meters is my guess. So I'm going to make them 8 meters long. That might be enough. And their thickness, at the moment, they're 25 centimeters. I think for an 8-story building, they have to be thicker than that. I'm going to make them 40 centimeters at the base. And so our shear wall will look something like this. Concrete. That's a plywood shear wall that we aren't using. Okay, so in the X direction, we've got I as the designer am choosing to resist all the earthquakes on 2 shear walls in the core. Now in the Y direction, I'm going to use frames. So in the Y direction, we use moment frames. The material of the frame is going to be reinforced concrete. And now I choose how many frames I'm going to use. Well, I'm going to have frames like every, say, 8 meters. So I go back to the floor plan. I'm just going to make the frames a bit bigger. So the default option is a 2-bay frame. And this is what it looks like. Like here's a perimeter 2-bay frame on a rather boring building at my university campus in Wellington. I'm not proud of the architecture of this building, but I'm proud of the strength of the moment frames that are just on the perimeter of this building. So we go back to the floor plan, and I insert moment frames by right-clicking. See, now I'm putting the moment frames in, and let's assume we're going to have a total of 6 moment frames resisting the earthquake attack in the Y direction. There, you can see the frames now, can't you? Now let's go back to this tab, the lateral and the structural Y. I can choose how many bays per frame. I think I'd like 3 bays per frame, like that. And I can choose the bay length. The bays are just a wee bit long, so I'm going to make them 5.5 meters. There we are. And then I've got to tell the program the floor width supported by a beam. In other words, take this beam here. What length of floor does it support? Well, if these are 8 meters apart, then the floor width is 8 meters. And finally, we have to guess the depth of the column. Well, I'm going to guess 60 centimeters. So now I have finished the design of this building. I have to go to the results. Click on the results tab. And these are the results. Now, the first graph here is for the reinforced concrete walls. And the first thing we notice is this flashing red light. And that always means danger. And so I click on the flashing red light, and it tells me that I've got a problem with torsional resistance because the separation is only 17% of the building width. I've got to adjust until it's greater than 25%. Okay, so I've got to go back to the floor plan, and I've got to separate these walls a wee bit. And now I'm okay. It's not flashing. So I've got to make my shear core a bit wider. Okay, so now I go back to the results, and I've got the wind. These are the results for the wind, which we're not worrying about. These are the results for the earthquake ultimate, the design earthquake. And these are the results for the serviceability or small earthquakes. So the software is telling me that my design, the shear walls in my design, when it comes to the shear forces, they are operating at 41% of their strength. So they're a bit too strong for shear. When it comes to the bending moments in the wall, they're at 48% of their strength. And when it comes to the drift, that means the sideways movement in an earthquake, the drift of the building is 94% of what the codes allow. So my building is very close to what the code allows in terms of drift. Like if I make my walls a bit, well, look, I do want to reduce the amount of concrete I'm using. So I'm going to make my walls thinner. So now I've made my walls 25 centimeters thick, but see how the drift is more than 100%? My building, my structure is failing. So if I want to, the most efficient thing I can do is to go back to my walls and just make them a bit longer. There. If my walls are 9 meters long, then they only have to be 25 centimeters thick, and I'm okay. There's no red here. So now I've done a design in the X direction. That's what my walls look like in plan. Two 9-meter long walls. Incidentally, those walls can go anywhere in plan. Like say I decide I'm going to put a wall there and a wall, well, a wall say there. I go back to my results, and actually that has made it a little bit worse for some strange reason. The walls are failing a bit. So maybe I just have to make them a fraction longer and they would be okay. If I bring this wall in, it doesn't make much difference. So normally it doesn't make much difference where the walls are in plan. Now let's design our frames. Okay, we want to design all our frames here, resisting forces in the Y direction. We go to structure in the lateral Y direction. We look at results. Now, when it comes to our frames, they are failing because there's red here. And the worst situation is that under the ultimate earthquake, the bending moments in the frames are 170% of what the codes allow. The frames I've designed are too weak. And so I could add more frames in, or I could make my existing frames, stronger. So let me make the column and beams a wee bit deeper. They're 60 centimeters, 65, 70. There, they've got to be 80 centimeters deep. And now there's no red. The design is perfect. And so this is what that 8-story building looks like. The columns are quite deep, aren't they? They're 80 centimeters deep. Let me go to the results. And if I click on other results, it tells me the column depth of the frame is 80 centimeters and the width of the column is 48 centimeters. The beam dimensions are 80 centimeters deep and 40 centimeters wide. So now I have done this design. And that design is complete. But then I might say, I don't like these two big walls. I'd rather have say 4 shorter walls. So I go back to the floor plan. I add in 2 other walls. We'll just put them sensibly there. I go back to the results. Here are my walls. And of course, I'm well beneath the 100% of the code. I've over-designed my building. And so therefore, I can go back and I can reduce the length of the walls. They were 9 meters. They're 8. They can be 7.5 meters long. And so if we have 4 walls, they have to be each 7.5 meters long. And then we've got a good design. So that's all I'm going to discuss now, I think. I think I've really done enough talking. For questions and perhaps draw the lecture to a conclusion. Is that okay?
Okay. Very nice presentation about the resist, Prof. There are some questions. Is it only for Windows because Mac user cannot use this? Is it correct, Prof?
The software is written for Windows. And so if you want to use this software on a Mac, you've got to have it running in a Windows way. So you've got to change your Mac so that it'll run a Windows software. I'm sorry.
So there is no chance for Mac user, unfortunately.
Yes,
Only
there is. Yes, there is. There's several methods you can use. And
yes.
if you Google this problem, Google tells you several different approaches where you can run on Macs.
Yeah, but there are some way to deal with this in the internet, isn't it?
That's right.
Yes, thank you, Prof. Do you want to answer some questions, or you still need to explain this?
No, I need to go. I need to finish in about 5 minutes' time.
Okay.
And so I can answer questions. And what I suggest is that the participants download the software, and I will begin my next lecture by doing a bit more explanation and taking more questions.
Okay.
So yes, let's have a few questions just to finish with. And then I'm very sorry, but I have another commitment I have to do. And I think it's been long enough listening to me. I'm sure it's time for everybody to have a nice break.
Okay, Prof. Actually, there are many, excitement to use this resist. But of course, next week's we will still with Prof. Andrew Charleson for next week's in the same time, same day, Tuesday at 1 o'clock. So hopefully all of you following this serial courses by Prof. Andrew Charleson. Okay, Prof. Andrew, there are some question about this, about your presentation. The first one is from Afinsa Haikal. From Afinsa Haikal. I have question, Prof. Charleson. What about the earthquake resisting structural concept for building that have asymmetrical complex plan? What is the current common practice? Thank you.
Well, if you have a complex plan, that is not necessarily a problem, but I guess I'm going to talk about complex plans in my next lecture, actually, because if we do have a complex plan, we have to have strong horizontal structure, but we call them strong diaphragms. But if you have a complex plan, you want to try and get your structure reasonably symmetrical. It doesn't have to be exactly symmetrical. It has to be reasonably symmetrical, and you just use the principles I've given you today. And so I would encourage you to, for you to try design of your structure using resist, and maybe have some more questions for me next week.
Yeah, thank you, Prof. Since there is a resist, so everybody can try symmetrical, asymmetrical, complex plan, and so on. So next week's you have to come back to our webinar. Prof. Andrew, between this system of shear wall, brace frame, and rigid joint, what is the best system to use for middle-rise building and high-rise building? From Aldrin Fabiansyah.
The best system is to use shear walls. This system has by far the best track record of the three systems. So if your program and concept can allow it, then please try and use shear walls.
Okay. Okay, Prof. Widodo, do you want to add something? No, it's gone again. Okay, from Pak Hakim to Prof. Andrews, such that it has been said that many types of structures are offered. All are more directed to multi-story building, as we found out that ability of the community to build multi-story houses is not so much. Is there a cheaper and better structure model for simple building built in earthquake-prone area for communities? Middle down from Pak Hakim.
Well, thank you. That's a really important question. I think confined masonry construction is the safest and probably the cheapest construction to resist earthquake in Indonesia. So for single-story, double-story, three-story buildings that for housing, I would recommend confined masonry.
Confined masonry. Okay.
Confined masonry with your bricks or blocks, with your practical columns or tie beams.
Concrete frame
is the most suitable construction.
Okay, Prof. From Mrs. Vina, Surabaya, I wonder, it better to place the structural element to resist earthquake systematically? Are there more design consideration if we are about to design building with more dynamic compositions?
If
dynamic
you have
composition, yes.
Yeah, like if you have a dynamic form of your building, you still need to have your two structural systems in each direction, but they don't have to be placed symmetrically. You know, you are allowed to have some torsion in your building, as long as you don't get the red flashing light and resist. Your design is okay, and engineers will be able to do the detailed design for you. So You don't have to have your structure perfectly symmetric. It allows you to have a more dynamic configuration of your building. So look, that's the answer to my question. And look, I'm very sorry, participants, but I have to go because I'm going to give another lecture now to a university in Macedonia in Europe. And they will be waiting for me. And so I have to go, but I will look forward to joining you again next week.
Thank you, Prof. Charleson. There are many questions actually, but unfortunately, yes, it's here, and then maybe we continue this with this question next week.
Yeah,
Okay?
great. That would be excellent.
Okay, okay, Prof. Andrew Charleson. Thank you very much for your courses, your lectures today. It was very interesting to us, and hopefully everybody can join with us again next week on Tuesday on the same times on 13 p.m. Isn't it? So, Prof. Andrew, please come back again next week.
Okay, I look forward to seeing you all. So I'll say goodbye. Goodbye.
Okay. Okay. Thank you very much, Prof. Andrew. Goodbye.
Bye.
Goodbye.
Bye-bye.
Bye-bye.
Bye.
Thank you.